have Clay Cordova speaking about line defects and quantum numbers and anomalies.
Okay, thanks very much. It's good to see everyone wherever you are. Yeah, so that's my talk: line defect, quantum numbers, and anomalies, and we'll see what it's all about. Oops. So first, let me just say who is this work in collaboration with. This is work done in collaboration with Thomas Dumitrescu, my longtime collaborator on many things, and Daniel Brennan, who's a new hotshot postdoc at UChicago. So keep an eye out for Daniel. And it's based on unpublished work, but hopefully work that will appear very soon. So what are the main bullet points, the main results? So what we're going to do is we're going to describe a class of discrete 't Hooft anomalies in 4D quantum field theories. And of course, these anomalies could occur in any quantum field theories, but we'll be particularly interested in how to realize them and compute them in gauge theories. And these anomalies we'll see are very closely related to the quantum numbers of line defects. So one thing that we'll mean by that is, for instance, the statistics of lines. And the anomalies that we study can be computed from the spectrum of fermion zero modes in a monopole background. So this will be sort of our main computational hammer that we'll use, and I'll introduce that and remind you how it goes as we proceed. So before getting going, I want to highlight two very significant references for this work. So one is a paper by McGreevy, Swingle, and Kravik. And the other is a paper by Wang, Wen, and Witten. And essentially, a lot of what we're doing here is digging in detail to the paper by Wang, Wen, and Witten and understanding what they did and generalizing it in a different language. Okay, so let's just all get on the same page for a couple minutes about 't Hooft anomalies. So everybody loves 't Hooft anomalies. Why do we love them? One reason is that they're interesting invariants of renormalization group flows. So here, just once and for all, let me say that unless I clarify the term, by 't Hooft anomaly, by anomaly, I will mean 't Hooft anomaly. That is, only anomalies that involve true global symmetries. So there are lots of phenomena that are called anomalies, but here, most of the time, we'll be talking about 't Hooft anomalies with one particular exception that I will mention explicitly. And of course, the simplest examples of anomalies that everybody loves are for continuous global symmetry, either internal symmetry or Poincare symmetry. And we first encounter these in quantum field theory class in models of free fermions, where we compute them by one-loop Feynman diagrams. So probably just to flash and have everybody be on the same page, in a 4D theory with a current J for a U1 symmetry, we have this very famous triangle diagram. And we all know what it means. The triangle diagram tells us about the conservation of J in the presence of a background gauge field. So a non-zero anomaly can be viewed as an obstruction to promoting the classical background gauge field to a dynamical gauge field that is summed over in the functional integral. Let me also point out that this calculation of this triangle diagram tells us something more about this particular class of anomaly. It tells us not only that there's this obstruction, but also where do we find it? We find it in the 3-point function of currents. So it tells us sort of physically how to detect this phenomenon. Okay, so the big claim to fame of these anomalies and their use as tools in renormalization group flows and strongly coupled field theories is that they're invariant under all sorts of deformations. In particular, they're invariant under any symmetry, any continuous symmetry preserving deformation of a quantum field theory. So you could dial coupling constants. You could, for instance, add massive degrees of freedom. You can also change the energy scale, normalization group flow. You can, if you like, you can think that the change in energy scale, the RG flow, is kind of a combination of 1 and 2, roughly speaking there. And okay, so one way to argue for these famous matching conditions is via Hooft's spectators. So this robust property makes the anomalies calculable and useful, and we'll actually use these ideas when we want to compute anomalies soon. So we have some maybe complicated non-abelian gauge theory where we want to compute an anomaly. We'll do something to it to get to a simpler presentation of the theory, and then we'll be able to compute an anomaly in that simpler phase of the theory. Okay, so those very simple anomalies that you get in triangle diagrams, um, one way to think about them is that they have an integer classification. That means that they're characterized by a coefficient, which is valued in the integers. So in the example that I gave you of the triangle anomaly, that coefficient was the sum of the cubes of the fermion charges. And of course, it is interesting to explore anomalies that are classified more generally by finite groups. And in fact, much of the explosion of interest in the past 10 years about anomalies is basically the realization that there's a huge plethora of interesting discrete anomaly phenomenon. And there's a lot to learn about quantum field theory by really getting all this discrete phenomenon correct. Okay, but what's the catch? One thing that makes it harder, and one thing that we'll have to think about is that these finite type, these sort of discrete anomalies that we'll be interested in as we go forward, they're not so easy to see physically. At least not nearly as easy to see as the triangle diagram anomalies, right? The triangle diagrams, or more generally, one loop anomalies, show up in correlation functions of local operators at separated points. So they basically hit you in the head in the most basic observables of the quantum field theory, that is the correlation function. By contrast, when we're talking about these, when we're going to talk about these more sophisticated finite type anomalies, one thing that we'll be after is sort of a robust physical mechanism that goes beyond the mathematics to calculate these anomalies and understand physically what they mean. Okay, so let me, before going on, let me ask if there are any questions. I can't see the hand raised while sharing my screen, so please just interrupt me if there are questions. Okay. Okay, so let me give you an example of the kind of thing that we'll be looking towards. So let's start with the famous Witten anomaly in 4 space-time dimensions. So we consider a theory with an SU2 global symmetry and n Weil fermion doublets. Okay, so as is well known, in this theory, there's no cubic triangle diagram anomaly. But there are still interesting responses that we can probe in the presence of a background SU2 gauge field. So let me call that background SU2 gauge field. I'll call it A. And okay, so this is a well-known story, but I'll go through it just to set everyone on the same page. So for instance, we put the quantum field theory on S4. And if you want to do a gauge transformation, you could think of that as a map from S4, the space-time manifold, to the gauge group SU2, which is topologically the same as S3. So we have gauge transformations G that are maps from S4 to S3. And now there's this interesting topological fact that the 4th homotopy group of S3 is Z2. And this means that there is a class of gauge transformations that are homotopically non-trivial. So let's take G to be one such gauge transformation. And we can look at the partition function, Z, coupled to a background SU2 gauge field. And we can ask, how does it respond when we do this large gauge transformation? That is, gauge transformation by a G that's in this non-trivial homotopy class. And then what you find is this, this interesting rule. So you do a gauge transformation of A, and instead of the partition function returning to itself, it toggles by a sign. So you here have -1 to the n, where that n, I remind you, is the number of doublets, the number of Weil doublets in your theory. So this kind of unexpected sign in the gauge transformation rule is the anomaly. And here you see it's a mod 2 phenomenon. So it's present if we have an odd number of doublets, and it's absent if we have an even number of doublets. Let me also say that here, let me remind you that here I am discussing this anomaly as an Hooft anomaly. So the SU2 is a global symmetry of this problem. So this is not an inconsistency or anything. It's just a feature of the partition function. It does, however, mean that if n were odd, it would be inconsistent to promote the SU2 to be a dynamical gauge field. Now, of course, this can be generalized to other representations of SU2. The same sign occurs, for instance, if the dimension is 4r plus 2, I think, for integer r. Okay. So notice just a little fact that will appear later and was crucial in that paper of Wang, Wen, and Witten, that 4r plus 2 is not all even numbers. So if you've only studied the Witten anomaly at a kind of cursory level, you might be under the impression that it forbids a single All-fermion in an even dimensional representation of SU2, or it is present for such a theory. That's actually not true. It's present only when the dimension is of this form. Okay, so in the spirit of what will follow, let me kind of criticize this presentation of the anomaly. It's of course completely correct mathematically, but it's very abstract. And you might ask reasonably, what is the physics of this anomaly? We can't see it in the correlation functions of local operators. Do we really have to resort to this very abstract partition function? And in fact, Witten also gave, in a later paper, also gave a very nice physical understanding of this anomaly. So let's imagine that somehow we arrive in a phase where the SU2 symmetry is spontaneously broken. And we try to detect the anomaly there. So of course, we can do that because of matching. So the anomaly is present in this phase where the SU2 symmetry is spontaneously broken. And now the fields in this theory, because SU2 is broken, include some Goldstone modes. And these are maps from space-time to SU2, which is S3. Okay, now there's some interesting physics in such a Goldstone model. So imagine space. Let's try to understand what kind of solitonic particles there are. So we can imagine space itself is a large 3-sphere, just by putting some reasonable boundary conditions at infinity. And then there are non-trivial solitons, which are labeled by homotopy classes of maps from S3 of space to S3 of the Goldstone manifold. And the very insightful thing is that the basic soliton, that is the object with soliton number 1, is a fermion if and only if the theory has the anomaly. So that's the nice physical perspective on the anomaly, and that's very much in the spirit of what we're going to try to do going forward. So we'd like to characterize certain discrete anomalies in terms of the quantum numbers of some kind of object, like a soliton or some kind of heavy probe or something like that. Any questions? Okay. Okay, so then let's dig in a little bit. So let's discuss quantum numbers of lines. So what was this part of the title of the talk? So Maxwell theory, as we'll see, provides a very nice venue to explore quantum numbers of line defects and their connections to anomalies. So what do we mean by this? So line operators, we usually think of them as some kind of defect, but physically you can think of them as a heavy probe particle. And if you have a heavy probe particle, you might legitimately ask, is that particle a boson or a fermion? Okay, that's a very reasonable question, but you can ask, what was your prior? What did you mean usually when you thought about Maxwell theory? And typically when we think about Maxwell theory, we have in mind, at least implicitly, that the elementary Wilson line, that is something with electric charge 1 and magnetic charge 0, is a boson. And the elementary Hooft line, that is something with electric charge 0 and magnetic charge 1, that this is also a boson. We could then investigate what that implies for other lines, that sort of implicit assumption. So if you fuse them, the basic Hooft line and the basic Wilson line, you will get the basic dion with electric charge and magnetic charge both 1. And now something interesting happens, which is that there's an angular momentum in the electromagnetic field, half integral unit of angular momentum in the electromagnetic field. So that means that if you think that the Wilson line is a boson and the Hooft line is a boson, then the basic dion with charge 1, 1 is in fact a fermion. And similarly, you can work out by consistency now, what are the statistics of all the other lines in the theory. Okay, more generally now you can come up with some other versions of Maxwell theory that are not exactly the same as that version that we just discussed. So we have these 3 basic lines, the Wilson line, the Hooft line, and the dion. And duality transformations allow us to choose 2 out of the 3 to be bosons, with the other a fermion. So there's nothing special about saying Wilson and Hooft are boson and dion is fermion. You can choose any 2 out of the 3. But that sort of begs the question, if implicitly we had in mind that usual Maxwell theory had the Wilson line and the Hooft line bosons and the dion a fermion, how do we write the action? How do we modify the theory to get these other versions where, say, the Wilson line is a fermion? So let me now explain how that works. And we'll see that one way to make things transparent is to look at the theory on a curved manifold. Any questions? Okay. So why is it helpful to look on a curved manifold? Well, one reason that it's helpful is that a fermion couples to the spin connection on its world line. So we can look for a coupling that would produce this effect. In fact, it's actually easier to do a generalization of that. So Maxwell theory is what is known as a bosonic quantum field theory. That means that it can be placed on a non-spin manifold. Let me call that non-spin manifold X. So what's the criteria for saying that a theory is bosonic or fermionic, and how do you tell? So what you do is you look at the local operators. So when I say that Maxwell theory is a bosonic theory, what I really have in mind is that all the local operators in that theory have integer spin. And that means it's consistent to put that theory on a non-spin manifold. Okay, now an interesting question. If you're on a non-spin manifold, then of course there's no spin connection. And so what happens to these fermionic lines? Well, the answer is that in these fermionic lines, is that in this situation, the fermionic lines will be the boundary of a topological surface. And this is very analogous to, say, a Ramon sector operator in 2D CFT, which requires like a topological branch cut to make sense of its correlators. So it's not quite a local operator, but the dependence on the branch cut is very minor. Here we're going to see something pretty similar. Okay, let's draw a picture. So let's imagine, so here we have a line L. I've drawn it in blue. This is the world line of a heavy fermion. And we are in a situation where space-time is not a spin manifold. And there is a surface sigma, kind of topological surface sigma, that is attached to this line. And the world line action for the line, the thing that really makes it slightly not a line, is that there is this, this coupling here that I've written. So we've got an integral over sigma, this surface, of W2 of the space-time manifold. So what's W2 of the space-time manifold? That is precisely the second Stiefel-Whitney class of the space-time manifold X. It is the obstruction to there being a spin structure. So how do you understand this? Well, one quick way to check it is that if X in fact was spin, then W2 is d gamma, where gamma is basically the spin connection, or a mod 2 version of it. And then we can move this topological coupling back to being the standard world line coupling to the spin connection. This is the more general thing that exists in a non-spin manifold. Any questions about this?
So Clay,
yeah,
are you saying that these fermionic operators become non-genuine?
I forget what the precise definition of non-genuine is, but essentially, I mean, the important
Think about
point, though,
as if you cannot measure them because they are trivial in homology. The cycle is the boundary of
I just mean that that there is this. I mean, this is a very mild effect, this coupling to the surface, because, for instance, it only depends on this background field, which is W2 of X, right? The curvature is a background field here. It's not dynamical, but nevertheless, this term is there. We'll see some more perspectives on it as we go. But indeed, there is this dependence a little bit on sigma.
Thank you.
More questions? Okay, let's keep going. Okay, so now we actually know what we need to do to make the Wilson line into a fermion. So how do we characterize a Wilson line? So you could say that on a two-sphere surrounding the point source of the Wilson line, the point charge in space, the integral of star f is 1 in some units. So I'll suppress some 2 pi's and e's to make things simple. So if we want to produce the required coupling, we include a new term in the 4D action. Oops, that should have been, these m's here should be x's, I'm sorry. So we should have an integral over x of star f wedge W2 of x. So how does that produce? Let's just think through the geometry for a moment to see that that produces the thing that we want. So imagine the geometry of the previous situation. So we have the line L, and we have sigma coming out of it, and we have a two-sphere that's surrounding L. And around that two-sphere, the integral of star f is 1. And so then this expression reduces to the integral of W2 on the sigma that comes out of the line. Okay. So the upshot of this discussion is that a version of Maxwell theory where the Wilson line is a fermion instead of a boson differs from usual Maxwell theory by its coupling to curvature and topology, specifically by these kind of by this term that we've written here. And of course, we could have done a completely analogous thing for the Hooft line by, instead of having star f there, we would just have f. And so turning magnetically charged things into fermions. Okay, so it's actually quite useful to organize your thoughts about this discussion to view this construction in terms of the underlying one-form symmetry of Maxwell theory. So Maxwell theory has a U1 electric and U1 magnetic one-form symmetry, and these couple to the electric and magnetic charges of line operators. This by now it's supposed to be part of canon of quantum field theory, so I won't explain it more. And these symmetries are associated with couplings to background two-form gauge fields. Let me call them BE and BM. And these enter the action schematically as star F wedge BE and F wedge BM. So you could think that the thing that we did before, where we tried to toggle the statistics of the Wilson line or the Hooft line, these are special cases where BE or BM are tuned to be W2 of the space-time X. Okay, so now we come to an interesting thing.
Clay, I do have a question.
Yes.
going back to star F wedge W2.
Yeah, I mean, Greg, I'm being extremely sloppy about wedge and so forth.
Okay, let me ask, okay. Yeah, well, star F, my problem is that star F is not quantized. Right, star F, the cohomology class of F is quantized, right? It represents the, F over 2 pi represents the first Turing class.
Sorry, the integral of star F measures the quantized electric charge.
If I take star and I make a transformation of the metric, aren't I going to get a factor? I don't.
This means in path integral, this means that you're summing over the spin C connection. So schematically, you can. I mean, this is just a schematic picture, but what really means is that you're summing over the spin C.
Well, you can do it that way. I mean, yeah, it's all equivalent. But
sorry, I mean, okay. So
let's just go back to Gauss's law, Greg. Are you saying the quantization that I'm using is just Gauss's law? The integral over a 2-sphere of star F measures the enclosed charge, and I'm assuming that electric charges are quantized. We're in a U1 theory. So magnetic charges are quantized, and therefore also electric charges are quantized.
On the middle dimensional cohomology, there's a duality. And so in general, star would not preserve any kind of quantization condition. But on the middle dimensional cohomology, it sort of does.
okay,
I mean, it's inconsistent with,
Yeah,
I mean, it's
self-dual and anti-self-dual.
I'm not sure that's right, and I'm sure that's not right in the presence of electric sources, but okay, go on.
Okay. Okay, so there's actually
quantized on shadow. I'm reporting this comment.
okay.
Sorry, Greg, what exactly is your problem with this expression?
Star depends continuously on the metric. So maybe because we're at the middle dimensional cohomology as middle dimensional degree here, I guess if I make a conformal transformation, I can certainly see that that it cancels out. But
Greg, you normally take the kinetic term, which is F square or star wedge or star F wedge F, the thing that is normally called F mu nu square. Whenever you see F mu nu, just write F mu nu plus B mu nu, and then square it. That obviously makes sense.
well, that's, I mean, the action he's displaying is just fine. What I was getting at was it wasn't obvious to me that star F wedge W2 is a sign. That's what I was complaining about.
So your problem is not with this expression, it's with another one.
Oh, no. My problem was that, look, e to the I pi being sloppy, W2 wedge F, that is clearly a sign, okay? Because F is properly quantized. Star changes continuously with metric, for example. In general, star F doesn't, I don't see why that has to, even in the vacuum, if I look at the vacuum Maxwell equations, then star F is closed to form, so it descends to a de Rham cohomology class. However, if I change the metric, that cohomology class moves around. Okay? I don't see why it's quantized. Therefore, when we write star,
well, Greg, there's nothing special about F versus star F by electromagnetic duality. We know that to be true. I mean, we can argue about how the mechanics of it comes about, but if you agree that F is quantized, then I think you have to agree that star F is quantized.
I have heard of electromagnetic duality before, but
yeah, I don't need to tell you about it.
But I think Greg has a point. What you just said, Clay, is correct on shell, but you write here formulas for configurations in the functional interval, which would be valid also off shell. So on shell, indeed, F is both closed and co-closed.
Yeah,
There's no
and
difference
moreover,
between
in
F
the
and couple.
absence
But
of
off
magnetic
shell,
and
this is
electric
not true.
forces.
Let me think about this question.
So Greg, I spoke when you spoke, so I didn't hear you.
So okay, so now you're worried about the way that you're worried about saying this in the action, that you can write this as star F wedge W2, and that's the right thing to do.
Right, Nani puts it very well. In the action, DF is always 0. Okay, because we chose a duality frame, but D star F is not 0. It's not even closed. So for example, when you write star F wedge W2, well, okay, you mean some kind of integral lift of W2, and then you take
Yes.
a closed two-form representative.
Yes. This is what I mean. Yeah. I
Yeah,
mean,
I know
choose an
that's what
integral.
you mean, but it's ambiguous by D of something. Now you can't integrate by parts with D because star F is not equal to 0. So when you write star F wedge W2, it depends on a lot of stuff. And I don't see that it's going to be a sign. My only comment was you motivated by this by saying there's a sign. All you need is to introduce a sign. It's not going to be a sign. Moreover, it's going to depend on various choices you make to make perfect sense of that W2 of X.
Okay, so the very good. So let me make some backtracks to say how I can make sense of this. So I think we're all happy with making the Hooft line a fermion using this kind of construction.
No problem.
Okay, no problem. So if I only want to make one of them, okay. So then suppose I want to make just the Wilson line a fermion. It is probably correct, as Kentaro says, that a more technically correct way of doing that is to say that I have a spin C dynamical field. That's really what I'm trying to do with the offset by W2. The real tricky point.
I see what you're saying, but I still don't like the star.
But I still don't like the star.
Anyway, let me not derail your seminar. Go on.
Okay. All right. Well, anyway, one thing I was going to say is that the real tricky point. Well, okay. Let's keep going. So the okay. So there's of course an interesting other possibility for the statistics of the lines. And this is where the Wilson line, the Hooft line, and the dion are all fermions simultaneously. This is sometimes called all-fermion electrodynamics. I think that nomenclature came from condensed matter literature. And this is, of course, consistent with the line OPEs due to the angular momentum in the electromagnetic field. And in terms, if you think in our schematic previous discussion, what we're actually trying to do here is turn on BE and BM simultaneously in a way correlated with W2. And now the interesting point is that Maxwell theory has an Hooft anomaly when both such backgrounds are activated. So we should expect an anomaly in this case as well. And you can quickly deduce what this anomaly is by looking at the general anomaly for Maxwell theory. So this general anomaly for Maxwell theory looks like 1 over 2 pi integral over y BE dBm. So kind of mixture in Simon's term, where y x is the boundary of y. So y is a 5-dimensional extension of our space-time manifold, and this is the inflow action for the anomaly. And if you grind out what you mean by these substitutions that I was doing with BE and BM, you would find that the anomaly of all-fermion electrodynamics is W2 of X times W3 of X, where now W3 of X is the perhaps a little bit less well-known third Stiefel-Whitney class of the space-time manifold. Sorry, that should have been Y. Too many typos. W2 of Y, W3 of Y. Of course, they're for the inflow manifold. So that's an anomaly that is known for all-fermion electrodynamics. This is one way to think about how to get it. And one thing that's nice about this presentation is that the anomaly is really tied to the statistics of some kind of operators in the theory. So not only have we explained mathematically what the inflow term is, but we've also connected it onto some physically simple observables in the theory. Okay, so more generally, you can discuss coupling Maxwell theory to a general global symmetry group, G. And let me assume, for simplicity right now, that this is a connected simple Lie group. And you can ask, what quantum numbers are meaningful for the lines? Okay. That is, what should we focus on? What question should we focus on when talking about the properties of line operators? And the most naive answer that you could give is that a line L might be in a representation of G. This is the most naive answer you could give. And okay, this turns actually to not be the best question. And the reason is because there's a counterterm ambiguity. When you have a line L, you can always modify that line L by a flavor-Wilson line for G. And that flavor-Wilson line can be in an arbitrary representation. So that's a counterterm because G is a global symmetry. So that flavor-Wilson line is just some background, some coupling to background field. And you and I, when discussing L, we may differ by these choices. So for this reason, the question of what the exact representation is not the right question. So the right question to ask about is about the quantum numbers of lines that cannot be removed or cannot be changed by toggling such counterterms. If you like, this is the fractional part of the charge of the line. What do I mean by fractional part? What I mean here is that if G is not simply connected, then there are, of course, non-trivial projective representations of G. And the local operators of the theory will transform in ordinary reps, non-projective reps of G. That's what we meant when we said that G, the theory had global symmetry G. But the lines themselves can be in projective representations. And this projectiveness is the fractional charge of the line that's robust under changes of these counterterms. So the fermionic lines that we discussed before are examples of this idea. So we talked before about the fact that Maxwell theory is a bosonic theory. All the local operators are bosons. That is, they have integer spin. But the lines are allowed to be fermions with half integral spin. It's not a meaningful question to ask for the exact value of spin, because this can be adjusted by a counterterm. But the half integral versus integral nature is meaningful. Now you should contrast this with a theory that has both bosonic and fermionic local operators. In this case, there's now a counterterm with half integral spin that's available. And so in this situation, it's actually not meaningful to ask about whether a line is a boson or a fermion, because all the lines come in both varieties. Perhaps a slightly different take on this is to think about it in terms of the world line quantum mechanics of the line. So if we have quantum mechanics with symmetry G, that means we have local operators in good representations of G. However, of course, a fundamental property of quantum mechanics is that the states can transform in projective representations of G. The question of which projective representation in question is not exactly protected, since you can toggle it by the action of a local operator. But the fractional part, the fact that it is projective, or the different classifications of projective representations, mod non-projective representations, this is robust. And in fact, this is an Hooft anomaly in the quantum mechanics. So that's why it's so robust. And this surface term that we were writing on sigma, this is the inflow action for this world line anomaly in the quantum mechanics. Okay, so we've now seen something interesting. We've seen that all-fermion electrodynamics has an anomaly, or more generally, if you have Maxwell theory coupled to various global symmetries, you can find anomalies. You'll have interesting anomalies when the Wilson line and Hooft line carry fractional charges under these global symmetries, whether those charges are for spin or for some internal flavor symmetry. Now, of course, our main dynamical interest is not in Maxwell theory. We really want to study non-abelian gauge theories and their anomalies. But now we know a trick. We know that if you have a non-abelian gauge theory and you want to see if it has this kind of anomaly, you just add a Higgs field and get down into a Maxwell phase, and then check what are the statistics of the lines, or what are the quantum numbers of the lines. And from this, you can quickly read off what is the anomaly in your theory, or at least of this discrete type of anomaly that we've been studying.
I'm raising my hand.
Yes, Nadi.
I understand how the argument you just made works in one direction. Namely, you Higgs to U1 and you found an Hooft anomaly in the effective U1 theory, therefore it must be there in the full theory. But there might be additional anomalies in the full theory that are not visible.
Absolutely, absolutely.
They should still
Absolutely.
be there, but they will not be so easily visible.
Absolutely. So I'm talking about a pretty restricted form of anomaly, which is this kind of discrete, if you like, W2, W3 inflow type anomaly, where that can be mod 2 or mod n, as long as your Higgs field and you kind of appropriate Yukawa couplings and so forth like that, preserve symmetries in question, these kind of anomalies can be detected. Of course, there are more subtle phenomenon where which is invisible to this method. So it's just this restricted class that I'm trying to get at. Okay, so what's the setup? So we'll have a non-abelian gauge theory with some fermions and a representation of the gauge group, and we'll have a real adjoint Higgs field, and we'll let that condense to give a Maxwell theory in the IR. So schematically, we have some non-abelian gauge field F squared, some real adjoint Higgs field phi, so we have d phi squared. We have some fermions psi d psi. We have some Yukawa couplings, lambda phi psi psi, and we have a potential that's going to condense phi. Okay, so when we do this, it's actually immediate to read off the quantum numbers of the Wilson lines. Those are basically the same as the quantum numbers of the elementary fermions, because when phi condenses, it will make a mass term for the elementary fermions, and so those will be a model for the Wilson line quantum numbers. So basically, what we're boiled down to now is to compute the quantum numbers of the Hooft lines, and this can be done by studying the fermion zero modes in a monopole configuration. And there are multiple ways to skin this cat. So I will give one, but everybody has their favorite way of studying zero modes in monopole backgrounds. So let me just say that we'll ultimately find interesting phenomena in the case where the fermions psi are in pseudo-real representations. And this is a kind of technical interesting point in the study of the zero modes. We want a specific kind of Yukawa coupling that allows for non-trivial normalizable zero modes. And this means that the kind of fermions that we're interested in are in pseudo-real representations of the gauge group. Okay, so like I said, many ways to get at the spectrum of zero modes. One way to do it is to just use index theory, look at the Hooft-Polyakov monopole, and read it off. Bang, bang, boom. You can also do it more directly or equally efficiently by thinking in kind of an abelian phase of the gauge theory. That's a little bit more in the spirit of what we're doing. So I'll just say how that works. So let's consider a U1 gauge theory for to get our bearings with electron that is a Weyl fermion of charge q, and of course another one of charge minus q. And let's see what the modes that we get from that are. So if we're imagining that we started with a pseudo-real representation, we'll restrict ourselves to odd q. So for instance, as a UV starting point that you might be aiming towards, you could imagine that you had SU2 gauge theory with a vial fermion, million typos in these slides, in the 2n dimensional representation. And after Higgsing, you'd get electrons with charge 2n minus 1, 2n minus 3, 2n minus 5, etc. And now you look at what kind of zero modes do these fermions have in the presence of a monopole. And for each electron of charge q, you find q real normalizable zero modes. And these form an irreducible representation of dimension q under rotations. So that's sort of the basic fact to start with about fermion zero modes in the presence of a monopole. Okay, so that's been known for a million years, but now you can use these zero modes to determine the statistics of the 't Hooft line. So let's start with the example, an example motivated by Wang, Witten, and Witten's analysis of an SU2 gauge theory with a single vial fermion in a 4-dimensional representation. So this is a consistent theory. I remind you that this theory is not afflicted by the Witten anomaly that would make it inconsistent. So after Higgsing, what do we find? We find one electron with charge q, and one with charge q equals 1, and one with charge q equals 3. And therefore, the zero modes are in a singlet and a triplet. So we have in total 4 zero modes. And now we can focus on U1 rotations. So let's focus on U1 rotations to see the statistics. So we have these 4 zero modes, and so what are their U1 spin charges? So we've got one pair of charge plus and minus 1, and one pair of charge 0. And we can therefore group them into complex creation and annihilation operators. I'll call them A dagger, B, and B dagger. So A dagger will have spin plus 1, A has spin minus 1, B has spin 0, and B dagger has spin 0. And they have standard quantizations. Okay, so now off you go. So so you start with a Clifford vacuum, let's call it ket 0, and it's annihilated by A and B, and you build a Fock space in this usual way by acting with raising operators. So our main interest was to understand the spin. How can we do that? So let's compare the Clifford vacuum of, let's call the spin of the Clifford vacuum X, and let's compare it to the spin of the top state in this little module, which is A dagger, B dagger on 0. And this has spin X plus 1 because B has spin 0 and A dagger has spin 1. And now we want to require that these assemble into full representations of the rotation group. So that means that the highest charge and lowest charge must be opposites if they're in a good representation of the full representation group, of the full rotation group. So then you get this equation, X plus 1 is equal to minus X. So in particular, that means that X is half integral. So the Clifford vacuum has half integral spin. And then acting with the A daggers and B daggers, all the other states also have half integral spin. So the entire multiplet is a fermion. In particular, this means that the monopole in this theory is a fermion. Any questions about this analysis? Okay, so what do we conclude? So the SU2 gauge theory with a single fermion in the 4 has a non-trivial 't Hooft anomaly that we discussed before. This here's the inflow action with the same typo, integral over y, w2 of y, w3 of y. And this is actually the main conclusion of Wang, Witten, and Witten. We've just said their analysis in a slightly different way and explored it in a kind of different language. So this is very interesting. This is a gravitational anomaly. It depends only on the coupling to curvature. It's a gravitational anomaly in 4 space-time dimensions. So integer type gravitational anomalies only occur in dimensions 2, 6, 10, etc. But these discrete type of gravitational anomalies can occur in other dimensions. And of course, although we've used the Higgs field to flow to all-fermion electrodynamics and compute the anomaly there, we can now throw away the Higgs field if we want. We could gap it out with a mass term, and the anomaly that we've computed here will remain. So this is a property of the theory even without the Higgs field. So it's also fun to look back at the original Witten anomaly, which is present for a single Weil doublet. And you could ask, how does this occur or appear in this? So I remind you that this statement of Witten anomaly, since we're talking about the SU2 gauge fields as being dynamical, this notion of anomaly is different than 't Hooft anomaly. This notion is the version that makes the theory fundamentally inconsistent. And you can ask, how does that inconsistency, or where do you see a hint of that in this analysis? So in this case, you have a single Weil doublet. So after Higgsing, you would have a single real fermion B, which is a spin singlet. And you would try to quantize it using the only algebra that you could write, which is anti-commutator of B with B is 1. And here you, of course, find a famous interesting problem for this algebra, which is that there's no consistent way to assign fermion number. So this kind of funny ability, this inability to assign statistics, is a hint of something a little bit sick in this theory. So that's just an interesting comment, I think. Okay, let's keep going. So we've built up all this technology, and now you can readily compute a bunch of different discrete anomalies in general.
Could you step back? So I understand that there is this anomaly, this W2, W3.
Yeah.
Now, how do we see, if somebody told you that, how would you tell that what you should check is the quantum numbers of a magnetic monopole? And a related question is, how do you even define the magnetic monopole in this SU2 gauge theory? There's no meaningful tooth line there.
There's no meaningful, what was the last word you said, Nadi?
The SU2 gauge theory,
Yes.
The fermion in the four-dimensional representation is SU2 as opposed to SO3. So it does not have any meaningful tooth lines.
So
exactly
good. Yes, I don't. So that is actually kind of the whole point of this project in a sense, which is that I know what I'm talking about when I say 't Hooft line, Wilson line, statistics of those lines in the abelian phase, in the case where I add the Higgs field and flow to the infrared. Then I get a clear signal in terms of the statistics of the lines there. And that's a clear signal. Now you could ask, it's a great question. Okay, what's the signal in the UV? And that I actually don't know. So I actually don't know what is the
computation you did, Clay, was in the UV. You took it was very important for you that this was a Polyakov monopole, a 't Hooft Polyakov monopole, because you use the counting of zero modes and all that. If it is in the context of just a pure U1 theory, then I'm not quite sure what you mean.
Well, you can take a U1 theory coupled to fermions, to electrons, and look at
Let me rephrase the question.
Background.
Is your monopole a probe particle, or is your monopole a dynamical excitation of the system? In the SU2 theory.
In the SU2 theory, it's dynamical. In the U1 theory, it's a probe.
Okay, so now I can ask, well, that's the first thing I'm kind of puzzled, because this W2, W3 in the UV is in the theory which has that only as dynamical particles.
That's right.
The computation you did, I can understand it there. Now, I can ask the question, well, the way I originally phrased it. Somebody told you that there's a W2, W3. How would you tell, given that this is completely gravitational, that what you should check is what happens in the background of a monopole?
So indeed, let me say that I do not have a good answer to that question prior to flowing to the infrared. Prior to trying to do this this calculation in the U1 gauge theory coupled to some electrons. So I don't have a good answer to that. And I really don't have a good answer to that. It's a great question. I mean, it's a bit analogous, coming back to the original analogy that I was giving with the usual Witten anomaly, where the SU2 symmetry is a global symmetry. So in the Higgs phase, you can see the anomaly through the statistics of the soliton. But if you're not in that phase, you could ask, what's the cleanest signal of that anomaly? There isn't even really a soliton to make sense of before you're in that phase. So, and I'm not sure what the cleanest signal is. I mean, there are various signals, but that nice physical signal of statistics of the soliton disappears in a general phase of the theory, I think. And similarly here, I don't know what the simplest observable is in a general theory, let's say, even not specific to the SU2 gauge theory, but just a general theory that has this W2, W3 anomaly. I can say what it is in terms of inflow. I can say what it means for the response of the partition function. But the notion that you should look at the statistics of some particular particle, that I think I'm really using heavily, that I can identify those particles precisely in the Maxwell phase, in the kind of abelian phase that I cooked up. So that's a very long-winded answer, basically saying I don't know a good answer to your question.
But normally when we have such a Hooft anomaly, given in terms of background fields, then a clean way to see which defect will carry funny charges is to use the expectation value of the background fields in some of the expression. So you have an anomaly expression, which is F, wedge something, whatever. And then you say, consider a configuration where the first F is non-zero, say because we have some kind of a defect. And then we read off the anomaly on the defect from the remaining terms. The thing that I find puzzling here is that I don't see any dependence here on the U1 gauge field. So if that anomaly would have been something proportional to F of the U1, I would say fine, when F of the U1 is non-zero, the remaining factors give me an anomaly in the quantum mechanics. But you don't have that. This term is purely gravitational.
Okay, it's a good question. Let's keep going, and we can talk about it more afterwards. I'm not going to get up.
I do not mean to derail your talk.
No. I understand. It's a good question. Yeah. Okay, so let me quickly sort of get to the end. So we built up this technology, and you can use it as a kind of now that you have a hammer, everything looks like a nail. So you can use it to compute a bunch of different discrete anomalies of the type that we've been discussing. So for instance, we have lots of different examples, but for instance, one to throw out there is you could think about symplectic gauge theories with multiple fermions, multiple fundamentals, or Weyl fermions in completely general representations. So an example that sometimes has been discussed in the literature is SPN gauge theory with 2NF Weyl doublets. And then you could look at what's the global symmetry carried by the local operators. What's the G? So here you have SO 2NF mod Z2. And so, of course, that Z2 quotient, actually in some cases you don't even need it, but that Z2 quotient means that there are several different projective representations for lines that are possible. Also in this example, -1 to the F is part of the gauge group. So the local operators are all bosonic. So it's also, again, meaningful to ask about the integral or half integral spin of the lines. Okay, so if you flow to an abelian gauge theory phase, this is our main trick. It's clear that the Wilson line would be a fermion. So there's some fractionalization in the Wilson line quantum numbers. And on the other hand, if you quantize the modes around the monopole, you find that the 't Hooft line is a spinner of spin 2NF, which is also, of course, a fractionalized representation of this G. It's a projective representation of this G, which has the Z2 quotient there. And so this simultaneous projectiveness of the Wilson line and the 't Hooft line implies that there's now a discrete anomaly an interesting discrete anomaly in this theory that involves both the flavor symmetry and the spin. So that's a kind of slightly different version of a similar phenomenon that we've been discussing. So we've also explored examples with gauge groups spin n in matter and pseudo-real representations. And there are many examples involving time reversal symmetry, which I didn't really discuss that much. But in this case, the right question to ask is whether the monopole or the Wilson line is a Kramer's doublet. That's the correct notion of a projective representation in this context for time reversal symmetry. And in this case, you have a term that instead of integral over sigma of W2, you would have integral over sigma of W1 squared. That's the analogous inflow term into the world line quantum mechanics, the thing that's capturing this world line anomaly. Okay, so let me just conclude and then we can go back to these interesting discussions. So there are a bunch of different directions. So obviously we're computing lots of examples, but it's also interesting to ask what general phases are possible given such an anomaly. So of course we have some non-abelian gauge theory phases now. We have we have our main toolkit, which is the abelian gauge theory with various statistics for the Wilson and Hooft lines. We can also get gapped phases. So for instance, you can Higgs, if you start with the All-fermion electrodynamics theory, you can Higgs that theory and get to a gapped phase. But interestingly, because of the All-fermionness, if you want to bring down a heavy scalar and let it condense, that scalar has to be charged 2, it cannot be charged 1. And so therefore you get, for instance, a Z2 gauge theory that carries this kind of anomaly. And finally, let me just comment that another direction that we're sort of actively figuring out right now is how these different anomalies are reproduced in standard chiral symmetry breaking scenarios and what they imply for sigma model dynamics. Okay, so let me stop here. Thank you.
Can I ask another question following up on what I asked before? Because depending on your answer, I think I know the answer. Depending on the answer to the question I'm going to ask, I think I know the answer to the previous one.
Okay.
When you took SU2 with isospin 3½ and you Higgs the U1, the monopole you study, is it the lowest charge monopole in U1 given electrons with charge 1?
I think so, yes.
Okay, but then I see the answer, and I think that some of the things should be slightly revised. This is not a monopole of the SU2 theory. This is not the Hooft-Polyakov monopole.
Oh, you mean because that would have charge 2?
This is a monopole that carries magnetic charge of the SO3 theory, not the SU2. And then everything makes sense, because your theory does have such monopoles if you are in non-spin manifolds, because W2 of X would be the same as F.
Okay, this is a bit
or
faster.
The same as the W2
of
the SO3 gauge theory. So because the fermions are in a half-integer representation. And then everything makes much more sense. First of all, it can be detected in the UV by considering in a Hooft line, something that carries charge isospin 1/2, because that's the same as the monopole you study. And furthermore, if you look at the anomaly you wrote, W2 of X times W3 of X, W2 of X is really F. And therefore, it does do exactly what I said, namely you take the anomaly and you substitute the value of the expectation value, and then you read off the anomaly, which is nothing but W3 of X.
But W3 of X is the anomaly of what in this is
Hooft line.
No, but the anomaly of a line is something.
Let us first fix the normalization, so we're talking about the same thing. The SU2 theory has a Hooft-Polyakov monopole obtained, which is a dynamical object in the SU2 theory, obtained by Higgsing SU2 to U1. I emphasize that that monopole is not the monopole that you studied.
Yes, I agree with that.
I
agree with that. Mine is the yes, yeah, I agree with that.
That monopole, such a monopole, exists in the high energy theory only if you're in a non-spin manifold, because there's a correlation since you have half
Yeah,
integer
because
twice
yeah,
as
yeah,
three.
yeah, 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 I
So
understand.
there's a correlation between W. You can consider the theory as an SO3 gauge theory, provided the SO2, sorry, provided W2 of the SO3 is correlated with the W2 of X.
Very good. So far, so good.
Now everything makes sense because the anomaly that you found involves W2 of X. And using the previous equation I mentioned, it can be viewed either as F of the IR theory or as W2 of the gauge theory in the high energy theory.
So far, so good, except for I don't understand how you translate that W3 into the statistics of the defect. Because,
That I do not see, but at least we're talking about the same object with the same dimension. Namely,
okay,
the object
okay,
that you studied is indeed activated by the anomaly. I thought the
okay,
name
yeah,
of the
fair
game
enough. Yeah,
is
fair
to
enough.
try to find a defect which activates the anomaly.
Fair
And
enough.
then
Okay,
the remaining factors the remaining factor in the anomaly is an anomaly in the effective theory on the defect. And that indeed is what happens here, except that's not the way you described it.
okay, fair enough. I understand. I understand what you're saying. That makes sense.
Are there other questions?
May I ask about this mass of fermion? You allowed this term, which is where phi, you call coupling, right? So when you are Higgsian, you have a massive fermion. Does it influence your consideration?
Yeah, I that's why I have normalizable zero modes. Without the Yukawa couplings, I sort of don't know how to do this analysis because the zero modes would not decay at infinity.
I see. Okay. Thank you.
Other questions? If not, let's thank Clay again. And also in 2 weeks, Nadi will give a talk. So, thank you, Clay.
Thanks, guys.